Hello everyone, Dikshit here. In this video, we'll talk about my recent Linux kernel contribution. So in this video, we will cover what it takes you to write a device driver for Linux kernel, what is the process to submitting it, and how it lends to the upstream Linux kernel at the end. This video is not about a tutorial of how to write a Linux device driver. It's to walk you through the process of developing a driver from the scratch, what it takes you to be in a stage where you can start writing a driver, how you write a driver, what the things that you follow, and how you submit it to the upstream Linux kernel, and what is the process there, and what it takes you from the submission to the final merging of your device driver. We will go through each topic here in this format, that what is the idea behind making me this contribution, what is a device for which I have wrote the driver, how was the device driver development process, and what were the learnings that I acquired during this entire process. So motivation for me for writing this device driver was my love for open source. I was always intimidated by the people who are contributors or maintainers to such big open source projects like Linux kernel. So I has always wondered of what it takes for somebody to be a contributor or be an author or be a maintainer to such a large piece of software. One more reason behind was for me to try to understand how that contribution workflow looks like, because it's very large community. There are thousands of people contributing every day to such a big Linux kernel project, open source project, right? So how does the process looks like? How do they manage that entire development process? That's what I wanted to understand. One more reason for me to do this contribution is to do some meaningful contribution, not just fixing some typos or removing some extra spaces like that. For me to do a meaningful contribution by which I can understand some stuff as a part of Linux kernel and also be a part of such bigger project. We'll talk about the device for which we have wrote the driver now. So that the device for which this driver is written is an 3D magnetic sensor from Infineon. It is called TLV493D. It is a 3-axis magnetic sensor. Basically, there's a 6-legs chip you see. This chip is capable of detecting the magnetic field around all of these 3 axes around the sensor X, Y, and Z. It is communicating over I2C interface, and it reports this magnetic field values in a particular format over the I2C to the connected device. It also has a capability to detect the temperature, the die temperature. So the output data that can be received from this sensor is 3 axes of magnetic fields and 1 temperature. The sensor comes, this is a sensor chip. The sensor comes in a different modules format. This one is, I think it's called, this is from Infineon only, it's called Go module. And this is one, I think it's from Adafruit, it's available on Robo. And I have used this particular module in my setup. This module, this sensor is used in various use cases like joystick control, which you use in the gaming controllers or single joysticks. You can use the same sensor as a part of rotary encoders to control your no functionality. The same sensor can be used in anti-tampering solutions, where it detects the magnetic fields to derive whether there is any tampering happened or not. Apart from that, this particular device driver was not existing in the Linux kernel. It was there available as a part of library from the Infineon on the GitHub, which is in it's a library used by, you can use this library in Arduino or in microcontroller, where you can derive the same sensor data by integrating this driver in your firmware. The driver for this was not part of Linux kernel yet. So this was all about the device. We'll go through the device driver development process that I have followed. So as a part of pre-work, I have done some research and stuff based on which before writing the driver. So I downloaded the data sheet for this sensor module and went through it to understand what is the functionality this device is supporting, what are the interfaces, what are the various characteristics and specifications of the device. Uh, since it is an I2C device and it can have multiple data, right? It has a 3 axis of magnetic field and one temperature data. So there will be various registers, I2C registers, which provide various information, whether to write some configuration on based on what data to be, what format to be read, or in which format, which data we want to read. So that is provided as a different register set. So I went through the documentation that was available on the internet about this device. Then I understood where does this device fits into Linux kernel subsystem. So that fits into the IIO, this kind of sensors, this magnetic sensor, accelerometer, ADCs. These all are kind of devices which fits into the IIO subsystem of the Linux kernel. So I understood what is an IIO subsystem. I have created a separate video of me browsing the IIO driver to understand how it works. And apart from that, I have also went through a couple of magnetometer drivers just to get the common idea of what should be the design and framework of magnetic sensor. Then I followed some recent contribution made into this IIO subsystem to understand how does the community makes the conversation, what is the expectations from a contributor, what is the requirement of getting a new device added to the subsystem. So for that I have followed some recent contributions on the Linux kernel. Once I have done all this pre-work, I was ready for writing the driver. So to write the driver, I have used this setup. It is an Raspberry Pi 4B. I have the sensor module which I have ordered from Robo, and I have used a USB to serial converter to get the serial console logs on the computer. This Raspberry Pi is having a custom Yocto image generated by me. I have created a separate video of how you can make your own Yocto image, which is capable of give you a setup to do a kernel development. I also host an meta layer, which you can integrate, and once you have this meta layer in place, whatever image that you generate for this Raspberry Pi will be capable of writing the device driver on it. Once we are ready with the setup, it is time to come up with some driver design. What are the changes we are going to make? So in the driver design, I have identified what all areas where the changes will be done. So since we are writing the new device driver, there will be a new source file to be added. Since it's a new device driver, there will be a different kconfig options as well as a makefile option to include this new device source file as a part of compilation based on this kconfig option. There will be a device tree entry for binding, which will be added as part of documentation, and maintenance field entry for this particular device on my name. The overall driver looks like this. So we have this sensor module that it's been shown in the setup. We have sensor module which is connected to this hardware over the I2C bus, SDA and SCR. It is a power which is given separately. In the Linux kernel, since this communication of this sensor is happening via the I2C bus, there will be I2C bus driver based on the SoC. We have Raspberry Pi. So as Raspberry Pi has their own I2C bus driver, so that would be part of Linux kernel. On top of that, we would be writing an IIO driver. So IIO driver comprise of these many things. IIO subsystem, which is a way of how they populate this IIO kind of devices. It uses I2C client as a slave driver to communicate with this communicate to the sensor via the I2C master. So there will be an I2C client driver. There is also RegMag framework, we'll talk about that, why it's dotted also in this graph. Uh, the IO subsystem exposes CSFS entries to the user space to give the data which is coming from the sensor or to configure anything on the sensor. On the user space, we have written a test application which uses this CSFS which is exposed by the driver for reading the XYZ magnetic field and temperature channel values and setting up the trigger. So these all are given as a CSFS entries, and the driver which we wrote is touching these many areas of the Linux kernel. Our idea was to write a driver in this fashion where it uses RegMap framework along with the IIO and I2C client, but after closely looking at the I2C registers of the device, we decided to drop the RegMap implementation and we directly communicate with the registers and not using the RegMap. That's why the first version which I submitted was including the RegMap, but then later in the next versions we dropped it after discussion on the once we have set up in place and driver design figured out, it was time to start writing the driver. As a part of development process, we will first interface the sensor with the Raspberry Pi, and we'll make sure that we have enabled the correct I2C bus and the sensor device is able to communicate over the I2C bus. Here, using the I2C detect command, we confirm the same thing. After sensor is detected on the I2C bus, it is time to set up a workspace directory structure where we are going to post our driver files and do the development. We have created this workspace IIODRV folder where we are hosting a make file to compile this driver as a module and the source file which holds the device driver. This is the source file which contains the entire code for this driver. After the driver is developed, it is time to validate it. To validate the driver, we have created some test application which reads the magnetic fields data from X, Y, and Z channel as well as the temperature channel. It also uses the various CSFS IIO properties to set up some triggers to periodically read the data out from the sensor. At this stage, we have a full-fledged driver developed for this particular device and it was ready for the submission. Before submitting the patch to the Upstream Linux kernel or the mailing list, it is advised to check your patch through the scripts which are provided by the Linux kernel in the source code. The scripts are there to validate your patch. It checks the formatting, check the way you made the changes, whether those are as per the standard which Linux kernel uses or not. So one of such script is checkpatch.pl that has to be run on top of your patch file that will report if there are any issues with the formatting and the standard that Linux kernel follows. For the device rebinding checks made into documentation, that can be checked with the help of this make dt bindings check command that will analyze the device rebinding changes that you have made. So this script has to be run before going ahead with the submission of the patch. Now, as you know, Linux kernel does not have a mechanism of pull request or merge request, something like that. It follows a mailing list approach where every contributors who want to contribute to Linux kernel will have to send out their changes as mail. The patch will be part of that mail, and that mail has to be sent out to a particular subsystem maintainers and subsystem distribution list. So in our case, we had two types of changes. One is for the driver source file changes, which includes the driver source file, make file, and kconfig and maintenance entry changes. And other set of changes were part of the device rebinding, where we have introduced a new device rebinding file for this particular sensor. So those two changes should be go as a different patches. So that's how we have formatted. We have created two different pages, one for documentation subsystem, one for the IO subsystem. We have also created a cover letter which comprises the changes that this particular patch set including. So this is the patch that it looks like. So this is the first patch which is including the source file changes. This is for kconfig. This is the makefile change. This is the source file that we have introduced, drivers IO meter tlv493d.c. The other patch of this patch set 202 is DT binding patch, which is addition of a new YML file with this device tree binding. And on the top, 0th patch is a cover letter which describes what is this entire patch set is about. Upon submission of this patches, we got review comments, this many review comments from various reviewers and maintainers, and it was time to incorporate or answer those comments which were added by them. One of the comment was an answer to the query that I have posted along with this first set of pages submission, was about the rag map. Our first version of the patch was including the rag map based implementation that we have shown here, right? But once we have developed the entire driver, and the complexity which was being introduced after adding the rag map is not justifiable based on the functionality that we were achieving. This particular device has very limited registers and a specific way of reading the registers. Now, due to that, this rag map is not fully fitting into the entire structure. So I had added a query, the first page set only, that whether we should be using rag map along with the default approach, or we should only go with the single default approach. On that, the reviewers had suggested that we should discard the rag map part and we should only focus on the so that's why this is the dotted, because we have implemented this rag map earlier, but the final patch does not include the rag map based implementation. So in the patch set 1, we got those review comments that we have incorporated in V2 and we submitted the same. On V2 again, we got some comments which were related to functionalities, some typo mistakes, using some macros which were not supposed to be used in that particular use case. So that we have also managed and went to another version. Like that, we iterated over 6 versions of the same patch set, and at the V6 we got the approval from the maintainer, Jonathan, for IO subsystem, that this patch is good to go now. And this was the entire submission process. From this entire development submission process to Linux kernel and get the driver upstreamed, I have learned a few lessons which would be a key takeaway from this video. Would be to what should be the motivation behind you contributing to Upstream. That has to be clear to you. You should have the technical understanding that is required for that particular subject. You should have done some homework about the area where you are submitting, whether it's this subsystem or any different subsystem. Idea is to get some basic information of how this framework or how does this community converses, what is the expectations, how does the entire flow goes through. During the process, I think we should focus on collaboration. People at the open source community are very helpful. They are there to help you get your stuff to Upstream at larger audience. Sometimes we feel that those people are giving too many commands, or they are being too much picky. It's not like that. They are there to support you. So we should analyze our inputs on top of that and be collaborative to make sure that the contribution that we are making is accurate and can go forward. This review process it generally takes time because people working at open source are majorly taking so many things at the same time. So you should be patient to get your stuff reviewed, get your stuff merged. You should be polite with them or be respect the community. That this entire community is built on trust and respect, so you should do the same. So that was all about the process of how this entire driver got mainline. This is the source file of the driver in the Linux kernel. Upstream. This got released as a part of recent kernel version 6.18. This is the source file, and another file is the device to binding file, which is another documentation. So this was all about this video. I hope you enjoyed it. Let me know in the comments if you have any queries or concerns. I'm happy to help you. And do also let me know what you want me to cover in the next YouTube video. Then bye bye.